Assalamualaikum and hello everyone. My name is Muhammad Ilman bin Muhammad Nezeri and I will be presenting my final year project with the title of Optical Properties of S-Deposited Zinc Oxide on Bilayer Graphene on Insulator by Thermal Evaporation. In this presentation, I will be discussing on 5 parts, which is the introduction, methodology, result and discussion, conclusion, and lastly the future work for this FYP. Introduction. Nowadays, the concept of the miniaturization of transistor is considered to be really beneficial in enhancing the total performance of the silicon ultra-large-scale integrated circuits. As we know, these circuits have a lot of usage such as the optical devices, photodetectors, sensors, and the solar battery. As you can see in the diagram, based on the more than more technology, the size of transistor will be reduced, which allow more transistors to be packed onto a single platform in order to increase the performance of the computer power. He also predicted that the number of transistors will be doubling every 2 years. In addition, more than more technology is about the advanced heterogeneous integration on the single platform silicon where many functional devices are used onto a single chip. To realize this technology, it will be needed the different types of semiconductor in fabricating different types of devices such as the gallium arsenide, silicon carbide, and the zinc oxide. To enhance this integration of the different types of devices, an insulator between the material and silicon is needed so that it can isolate them to avoid any leakage and the short circuits. As we know, there were several semiconductors that can be used on the insulator in order to fabricate the devices such as the gallium nitride, gallium arsenide, silicon carbide, and also zinc oxide. However, in this experiment, we will be using the zinc oxide as the semiconductor, which is due to its advantage, such as has the large exciton energy with the 16 mV. It also has the wide direct band gap, which can make it has the higher breakdown voltage and has the ability to sustain the large electric field with the lower electronic noise. Besides, it also has the thermal stability at the room temperature, which can make it suitable to operate and stable at the room temperature. And lastly, zinc oxide also have the high transparency, which is this feature can make it transparent and well absorbed to the light. So this can make it really useful for the applications such as the solar technology. As we know, some electronic devices such as electronic displays or bioelectronic devices will need some unique features from the arbitrary substrate such as plastic and glass. The reason why we use this arbitrary substrate is because of their advantage such as the flexible, transparent, non-toxicity, and also chips. However, to do the direct growth of the semiconductor on insulator is quite challenging due to the amorphous structures of the insulator itself that can cause the lattice mismatch of hexagonal properties between the device and platform. Therefore, the graphene is utilized as the buffer layer in order to grow the zinc oxide with a high quality due to its flexibility and the strong characteristic. The main reason we use the buffer layer is to grow the semiconductor with a high quality and to reduce the lattice mismatch between the zinc oxide and the substrate. In this study, we use the graphene as the buffer layer due to its advantage such as the good conductor and have the zero energy bandgap. Graphene also have the ultra high mobility which is up to 200,000 cm² per volt. Graphene also have the high thermal conductivity which is 10 to the power of the 3 watt per meter Kelvin, which can make graphene is resist at a high temperature. Besides, graphene has the similar hexagonality structure with the zinc oxide, which can make to grow high quality zinc oxide on the graphene become more possible. This slide shows the possible deposited mechanism of zinc oxide layer on bilayer graphene on glass in schematic. As you can see, this is the top or the bird view of the CVD bilayer graphene on glass, where the CVD graphene had been transferred onto the glass substrate to be bilayer graphene on glass. From the cross-section bilayer graphene on the glass, we can see that there might be the existence of the boundaries in between the graphene islands. The next one is the cross-section during the deposition process where we deposited zinc oxide on the CVD bilayer graphene on glass. Lastly, we can see the cross-section of the deposited zinc oxide layer on bilayer graphene on glass as there is a black layer on top of the graphene and glass. As for the deposition method, basically there are several methods to do the deposition or to graph the zinc oxide on graphene on insulator. However, in this experiment, we had used the thermal evaporator since it is the most simplest way compared to the others, as we only need one solid target, which is the zinc oxide powder. Other than that, by using the thermal evaporator, we only apply the low temperature onto the substrate so that we can do the process of deposition directly onto the low melting point substrate, such as the plastic or rubber. Besides, the thermal evaporation technique will produce less toxicity along the experiment compared to the other CVD techniques. Lastly, the advantage of this CVD techniques is considered low cost since the equipment that had been used is quite simple and only one target required for the result. The main objective for this FYP is to deposit the zinc oxide on graphene on glass by thermal evaporation technique and characterize it. For the scope, we want to do the deposition of zinc oxide with a thickness of 500 nm on graphene on glass substrate by using the PVD technique, which is the thermal evaporation. We also want to measure the thickness of deposited zinc oxide by using the surface profiler. And lastly, we want to analyze the optical properties of deposited zinc oxide by using the photoluminescence spectroscopy. This is the process flow for this experiment where first we do the substrate organic cleaning by using the acetone and ethanol for about 15 minutes, and then we rinse the substrate with the DI water to remove all the contamination. Then we do the deposition process by using the thermal evaporator, where here the targeted will be the zinc oxide powder with a thickness of 500 nm. Lastly, we followed by the analysis by using the two equipment, which is the surface profiler and the photoluminescence spectra. This is the Raman image of the Bilayer graphene on glass that we use in this experiment. We measure the Raman spectra at the 4 different points. As you can see from the graph, based on all of the points, the 2D mode and the G mode were strongly emitted at the 2670 cm3 and 1580 cm3 respectively. The ratio of the 2D and the G peaks also was around 1.03, which indicate that the graphene that we use here is bilayer graphene based on the condition here. For the deposition process, the substrate that we use is bilayer graphene on glass with the dimension of 1 × 0.5 cm, while the targeted is zinc oxide with the percentage of 99.9%. The density that we use is 5.61 grams per cm3 with the Z ratio of the 0.556. The desired thickness that we want is about the 500 nanometer. Here is the setup of the thermal evaporator with its schematic diagram. In order to do the deposition, the substrate was put onto the stage while the zinc oxide was put onto the board. The board will be heated up by passing the high electrical current to the clamps that connected to the high current source. The deposition rate was controlled with the applied current, where here we apply the current for about 43 to 57 ampere. The zinc oxide then will be evaporated in a vacuum to allow the vapor particles to travel directly onto the substrate where they condense back to a solid state. As for the analysis of sample, I am focusing more onto the thickness and the optical properties. For the equipment, I use the Raman spectrometer to identify the graphene layer of the substrate. I also use the surface profiler to identify the thickness of the deposited zinc oxide. And lastly, I use the photoluminescence spectrometer for the optical and electronic properties of the materials. So the next will be result and discussions. As you can see, in the first result, we managed to deposit the zinc oxide with a thickness of 500 nm on graphene on glass. The deposited zinc oxide is in black due to the oxygen deficiency and have the large number of defects after the deposition process. The next result will be from the surface profiler. Based on the software result, we can see that the average of the graph height is around 500 nm, which indicates the thickness of the deposited zinc oxide. The last result will be from the photoluminescence spectra of the deposited zinc oxide. Based on the graph, we can see that the UV emission was emitted at 3.26 electron volt with the wavelength of 380 nanometer, which indicate the optical bandgap for this deposited zinc oxide, while the visible emission was emitted at 2.18 electron volt with the wavelength of the 570 nanometer. From here, we get the intensity as 54% of the green luminance at the visible region with the band edge emission intensity at the UV region by using formula IUV divided by I visible. The intensity is due to the defects such as O vacancies and zinc interstitial, and these defects are responsible for the recombination of the green luminance. From the summary of this work, we can see that the optical band gap is comparable with the other previous work. Although the deposited zinc oxide has a low of oxygen content, the ratio is quite high compared to the deposited zinc oxide, which means that there is lower number of the defect. The next part will be the conclusion. As we can see, zinc oxide with the 500 nanometer thick was successfully deposited on bilayer graphene on insulator by using the thermal evaporation technique. The deposited zinc oxide layer on graphene was in black due to the oxygen deficiencies, so an oxidation treatment will be needed to increase the oxygen content in the zinc oxide layer. Also, a strong emission with the peaks at the UV and visible region are emitted at the 3.26 electron volt and 2.18 electron volt respectively. The ratio of the IUV and I visible is around 54%, which is due to the oxygen vacancies and the defect density. There will be also further analysis on the deposited zinc oxide and oxidation treatment. The last part will be on the future work. A comprehensive study on characteristics such as morphology, crystallinity, transmittance, and electrical properties on as-deposited zinc oxide is really necessary. Besides, the zinc film was in black after the deposition process. This is due to the lack of oxygen level in material itself, which could give the negative effect to the good properties of the zinc oxide. Therefore, an additional treatment is needed, such as the oxidation. The treatment will increase the oxygen contents in the zinc film to be more balanced in the zinc and oxygen level in zinc oxide layer, which then can increase the quality of the deposited zinc oxide. One of the techniques that can be used is by using a dual-zone furnace where the oxygen gas will be flew into the quartz tube through the process. I guess that's all from me. Thank you.